Welcome back to Inorganic Chemistry. In this chapter we'll discuss symmetry of molecules, how to describe it mathematically, and how to apply it. In this first part we're going to look at symmetry elements and operations and how we can put them together to describe molecules using point groups, and then how those point groups are further described in character tables. In our next part, we will look at applications of symmetry, in particular molecular vibrations. So we've seen different ways to represent the water molecule. For example, when we learned about Lewis structures, and we saw a condensed line drawing model, and then a model that represents the three-dimensional geometry with the oxygen in the center and the two hydrogens. And we learned from valence shell electron pair repulsion theory how to describe this as a bent molecule. And we can use a computer to generate space-filling models. What I'd like to do today is to work with actual three-dimensional models so that we can learn about the ways in which we mathematically describe the symmetry of any three-dimensional object, but of course in chemistry we're interested in molecules. So to understand how to describe symmetry, we need to learn some vocabulary. So symmetry operation is how to move the object in such a way that it looks unmoved. Or unchanged. So for example, if we look at our water model here, you see the bent geometry with the oxygen in the center and the two hydrogens. If I move it, it's not quite perfectly symmetric. Of course, this is a real world example. If I move it in such a way, I can move it so that it looks changed, right? If I move it like that, well, it's rotated and translated. It looks different than when I first had it here in this position. But if I rotate it 180 degrees, for example, then it looks like I didn't do anything, like it didn't move it at all. So that rotation 180 degrees would be an operation that describes the symmetry of this molecule. I can rotate it 180 degrees and it still looks the same. Now the next vocabulary word is the symmetry element. And the symmetry element is the geometric entity about which the operation takes place. The symmetry operation takes place. So if we look again at our example of the water molecule, and it has this 180 degree rotation motion, the element about which this rotation takes place would be an axis. So an axis right here going through the center of the oxygen is where this 180 degree rotation takes place. So that would be a rotation axis. So there's a whole bunch of collection of these that we use to completely describe the symmetry of objects. And to summarize these, we talked about rotation. Well, we can describe that rotation in terms of how many degrees that rotation is. So my 180-degree rotation, I could say, well, it's a 180-degree rotation, or I could say it's 360 divided by 2 is 180. So the 2 is the important part. I would call this a twofold rotation, or C2 rotation. And that rotation takes place about the element of an axis. We call this a proper rotation axis, and it has the same symbol, C2, corresponding to the type of operation. Okay, what other types of elements do we have? We have reflection is an operation. Reflection is like a mirror. If I take my hands here and I have them, well, these aren't perfectly mirror images because I have a ring, but in general, your right hand is a mirror image of your left hand. And so I can imagine reflecting here to create this mirror image. In the same way, if we look at the water molecule, we can see that this half of the water molecule looks exactly like this half of the water molecule. So if I were to reflect or had a mirror here, it would look like I didn't change the molecule. So there's reflection symmetry for the water molecule, and the element for that symmetry operation of reflection is a plane. A plane perpendicular here to the molecule, and since it, in general, we think of it as acting like a mirror, we call it a mirror plane. Now there are different types of mirror planes. There's a horizontal mirror plane. A horizontal mirror plane is one that is perpendicular to the rotation axis. So here with the water molecule, we saw there's a rotation axis here and there's a mirror plane here. So that mirror plane and the rotation axis are actually parallel. So the correct type of mirror plane for a water molecule we would actually call a vertical mirror plane, because it is parallel to the rotation axis, the primary rotation axis. There's a third type of mirror plane called a dihedral mirror plane, and this mirror plane bisects the C2 axes, or bisects the axes. This molecule doesn't have that, so I can't demonstrate with this molecule. But we could demonstrate it with this molecule. This is a representation of the structure of methane. And methane has a rotation axis here, C3. If we rotate it 120 degrees, we get the same, it looks like I didn't move it. So that would be 360 divided by 3, so that's a C3 rotation operation taking place about a C3 rotation axis along this bond here. There's the same thing if we rotate the molecule here, we get the same thing. If we rotate the molecule here, we get the same thing. And if we rotate it here, we get the same thing. So we have a bunch of C3 axes. And we have mirror planes. We have a mirror plane here. This half of the molecule looks identical to this half of the molecule, so the reflection of this half forms that half. It looks like we didn't change anything, and that took place around a mirror plane. And this mirror plane includes that C3 axis, so that would be a vertical mirror plane. Actually, the best molecule to represent a dihedral rotation, or dihedral mirror plane, is tetrachloroplatinate. which is a square planar molecule. So, if we look at this drawing of a square planar molecule, so the platinum is in, and the chlorides are all in the plane of the paper. And if I'd drawn this perfectly, it would have made a square, so that's why the geometry is square planar. And you can see that there is a rotation right here. I can rotate, if I had a true square, I could rotate 90 degrees and it would look like the square again. I could rotate 180 degrees, and except for the letters being upside down, the atoms don't have the orientation like my letters, and so it would look like I didn't change the molecule. And I could rotate it 270 degrees and it would look like I didn't change the molecule. So we have here rotation, multiple rotations. We had 90 degrees, which is C4. We had 180, which is C2. And then we had 270, which is C4 3 times. So we could talk about that we cubed the C4 rotation. We did it 3 times. C2 is actually doing the C4 rotation 2 times. So all of these operations take place about the C4 primary rotation axis. Right here. So we have one element, the axis, multiple operations, but you can see they're all the same type of operation. They're all multiples of the C4 operation. Okay, let's get back to our dihedral mirror plane. Where is this dihedral mirror plane? The dihedral mirror planes are defined as parallel to the primary rotation axis, but bisecting the C2 axes. And in this molecule, there's a C2 axis here and a C2 axis here. If I rotate 180 degrees about that C2 axis, this chloride goes where that chloride was, and it looks like it didn't move anything. So if I can imagine here, right through here is a mirror plane, because if I reflect the bottom half of the molecule, it looks like the top half of the molecule. When I do that reflection operation, it looks like I didn't move anything. So there's a mirror plane here that bisects these 2 C2 rotation axes. So that is a dihedral type mirror plane. And there are many other mirror planes in this molecule which we'll see in a little bit after we finish looking at our elements and operations. Okay, so another operation is inversion, or to invert the molecule around a center, and that would be the element, the inversion center. They both operation element have the symbol I. Another operation would be to rotate and then reflect in a way that's perpendicular to the rotation you just did. So let's write that, reflect perpendicular. This symbol is S sub n, so it's the same n index telling us how many, what fraction of 360 we rotated. But then the S distinguishes it from the C, because this is not a proper rotation, this is an improper rotation axis, meaning, well, it's hard to see unlike the proper rotation axis, there is a rotation there, but it's hard to see because you also have to do the reflection in order to realize the full symmetry. And finally, to round things out, this is all derived algebraically using group theory and matrix algebra. There is the operation where you look at the identity of the molecule, or in other words, you don't do anything to it. So here's my water molecule, I don't do anything to it, and of course it still looks like I didn't do anything to it. So that's called the identity operation. It has the symbol E. There's no element for this operation. All of space, I guess, in a sense, would be the element because the object is in space, but we're not moving it at all. Okay, let's get back to our platinum molecule. There's a few more things to illustrate here. And we looked at the C2 axes. We looked at the sigma D. Oh, and these C2 axes here. These C2s are perpendicular. We saw earlier there's actually a C2 right here. And these C2 axes are perpendicular to that. So to distinguish the axis from this axis, we're going to call it C2 prime, C2 double prime set of rotation axes. There's also vertical mirror planes. So if I had drawn this perfectly, we reflect this side of the molecule to this side of the molecule. It looks the same. So there's actually a vertical, there's a mirror plane here, and that's vertical or parallel to this C4 primary rotation axis. So there's a sigma V here. And there is a horizontal mirror plane. So a horizontal mirror plane is perpendicular to the primary rotation axis. Here's again a C4 primary rotation axis. And we started out saying this is a square planar molecule. It fits in the plane of this paper, which is perpendicular to this rotation axis. So the plane of the paper is a mirror plane. We reflect the top half of the molecule to the bottom half of the molecule, cutting right through the atoms. And so the entire paper here is a mirror plane, and we call it sigma H because it's a horizontal or perpendicular to that primary rotation axis. So you can see there's a lot of symmetry in this molecule. How do we figure out the symmetry of a molecule with so many options to look at? Well, in many texts is a flowchart to help you organize how to approach this problem to determine the symmetry of a molecule. And I've devised a flowchart here as well. So first you could say, is the molecule linear? If it is linear, then you want to ask, is there an inversion center? If there is not an inversion center, then the type of molecule is C infinity V, or the type of symmetry. If there is an inversion center, then it's D infinity H. Okay. Is there a rotation operation or rotation axis? Yes, if there is a rotation axis. Is there more than one rotation axis with an index greater than 2? 3 and so on. So n greater than 2. If there is, does it have an inversion center? Wait, I got this backwards. No, if there's no inversion center, then you have a highly symmetric molecule called a tetrahedral, or T sub D. If it is symmetrical, or if there is inversion, then the next question is there a C5 rotation axis? If yes, then you have an icosahedron type geometry. If no, then you have an octahedron. Now let's look at an example of a tetrahedron here. Is our methane structure. We saw before, multiple C3 axes, but we do not have an inversion center. If we look at the center of the molecule, if we invert, this part of the molecule goes through and over here. This part goes through and over here. This part goes through and over here. This part goes through and over here. So that would look like this, which looks like I moved the molecule, because I indeed did move the molecule. So this methane is not symmetric with an inversion operation, and so it is highly symmetric, but not that type of symmetry, so it is a tetrahedral shape. Okay, what if we have C2s? We don't have more than one primary rotation axis. We only have one primary rotation axis. Do we have any C2s that are perpendicular? Remember we had that C2 prime perpendicular to our primary rotation axis. If yes, then we go over here and we ask, is there a horizontal mirror plane? If yes, then we have DNH, which is what we saw with our squared planar molecule. If no, then we ask, are there dihedral angles, dihedral mirror planes? If yes, then of course we have a dihedral type symmetry. If no, then we just have D indicating there's a C rotation axis and then there are perpendicular C rotation axes. Okay, let's go back. What if there's, no, we don't have C2 axes perpendicular to primary rotation axis. Well, we can ask again the next question. Do we have a horizontal mirror plane? If yes, then we have C and H. H again indicating it has a horizontal mirror plane. No. Well, do we have vertical mirror planes? If yes, then we have C and V vertical. If no, maybe we have an inversion center or improper rotation axis. Then we'd be here. We have an S-type symmetry where the N is twice actually this primary rotation axis here. If no, then we just have a molecule with rotation. Okay, what if we don't have any rotation at all? No. Do we have a mirror plane? If yes, then do we have inversion? So it's kind of the same flowchart. We ask about rotation, mirror, inversion. If we do have inversion, then we have a molecule with inversion symmetry. If we do not have inversion, then we have a molecule with only mirror symmetry. There's one mirror. If we have no mirror at all, we have a molecule with no symmetry. And an example of that would be this molecule here, where we have, it's like methane, but we have 4 different substituents around the carbon, and so we do not have rotation symmetry, because if I rotate, any way I rotate, you can see the colors change on the corners of the tetrahedron. And I don't have a mirror plane. If I reflect, then the color changes. The purple would go where the light blue is, and so that's not symmetric. So this molecule has no symmetry, it's CS. So thank you for your attention. Next time we will talk about how to apply symmetry to molecules to learn about chirality and vibrations.